we had seen that shortest remaining processing time first was optimal with preemption. But I fear I lost some of you on the rounding step. So once we get that preemptive schedule, how do we actually produce a schedule that does not involve preemption? And my claim was that you should simply schedule all the jobs in completion order. And that this would be a 2 approximation. Okay, but I think my explanation came out a little scrambled. So let me show why this works. So the idea is that I'm going to do this in a sort of a contorted way. What I'm going to do is I'm going to take the preemptive schedule and then at the moment that J completes, I'm going to insert PJ idle time. Okay, so I'm going to take this schedule and I'm going to sort of add empty space in the schedule. Okay. Now, since I've inserted PJ idle time, that is sort of allowing, that's room that I could use to schedule job J non-preemptively. Right? So by inserting all of these spaces in the schedule, I've created enough space to create a non-preemptive schedule in the order of job completion. And the question is, what does this do to the overall, to the completion time of job J? Okay. And this is where we leverage the structure of the preemptive schedule. Okay, because the preemptive schedule is sort of feasible, right? Since I'm looking at all of the jobs in order of completion, right? There's a certain collection of jobs that completed before job J. And these jobs completed before job J in the preemptive schedule, right? So what I'm going to be doing to CJ is adding all of the PK where K completes before J. Right? Because I'm inserting these idle spaces in the order in which jobs completed. So the idle spaces that come before job J are precisely the jobs that in the preemptive schedule finished before job J. Right? And so the total space, the total inserted, the total delay in CJ is therefore equal to the sum over K finishing before J of PK. Right? But what can I say about the total processing time of all of the jobs that finish before job J? Well, in the preemptive even in the preemptive schedule, if they finished before job J, it must mean that all of their computation got done before job J. So in the preemptive schedule, there is this much processing happened before job J, right? And so if this much processing happened before job J finished, that means that this total amount of time must be less than or equal to the completion time of job J. Right? And so that's the key of the argument, is that the amount of delay that I'm introducing in job J by going to a non-preemptive schedule is bounded by the total amount of processing that happened before job J in the preemptive schedule. Right? And so the increase in job J's completion time is only another factor of CJ. In other words, at worst, it doubles. So each completion time at worst doubles. And that means that overall, your average completion time at worst doubles. And so you have a factor of 2 approximation. OK? Yes? Why this?
Why is it at most 2 times?
Well, so remember, what we're doing here is we're looking at all of the processing times of jobs that finished before job J on this one machine, right? And that total processing time, right, that's all holding up J in the preemptive schedule, because all of those jobs finished before job J. So if they're all coming before job J in the preemptive schedule, before the completion of job J, that means that the amount of work that was done before job J completed is this quantity, or is at least this quantity, sum of pk. But that all happened before job J completed, so it has to be upper bounded by Cj. Okay? So hopefully this time that argument is clear. Are there still questions about it? Okay. So last time we looked at a couple of really clever and interesting relaxations for some of the problems that we wanted to approximate. And this is a very common approach to doing approximation algorithms, is you stare hard at the problem and you figure out some problem that is like it, a good relaxation, but that is tractable. Okay? But today we're going to focus on a cookbook method for relaxing problems. So you don't have to think about what the relaxation is. Unfortunately, you still have to think about how good your approximation is, but at least we've automated some of the process of coming up with an approximation algorithm. Okay? And I'm going to introduce this by way of an example. So let's go back to vertex cover. Okay, so this was the problem where you wanted to pick a collection of vertices in a graph so that every edge had at least one of its endpoints picked. So these chosen vertices together cover all of the edges in the graph. Okay? And we developed a sort of super greedy two-approximation algorithm for this problem, where we repeatedly took both endpoints of an uncovered edge. Today I'm going to show you a different algorithm. Okay? And it's based on the idea of linear programming. Okay? So let's write down a linear program that captures this problem, or that starts to capture this problem. So what I'm going to do is I'm going to write a bunch of variables, xi. Xi is going to be equal to 1 if I choose I, if I is in the cover, and 0 if it's not. Okay. So if I have these variables, how can I write down the size? What would be a formula for the size of the vertex cover? The sum of the xi's. So my goal is going to be to minimize the sum of the xi's. But now I have these constraints that I want to cover every edge. So one of the endpoints, at least one of the endpoints of each edge has to be chosen. How can I write down that constraint mathematically? Yeah?
For all ij in edge set, xi plus xj is greater than or equal to 1.
Good. So I just say xi plus xj greater than or equal to 1 for all ij in the edge set. Okay. And look at that. I've just written down a linear program that represents the vertex cover problem, right? So if I can go off and solve this linear program, I'll have a solution to the vertex cover problem. But this should sort of make us pause, because we said that vertex cover is an NP-hard problem. So I'm not going to suddenly reveal that P equals NP in the middle of an advanced algorithms class. So what's going on? Yes?
The xi should be 0, 1. Not
Yes. So this minor detail that the xi's should be 0 or 1 is changing the complexity of the problem. So what we have here is what's called an integer linear program. Which, as you might imagine, is simply a linear program with integers. Okay? And I've just shown you how to write down vertex cover as an integer linear program. But what this immediately tells us is that integer linear programming is NP-hard. It's actually NP-complete. It's in NP as well as being NP-hard. So what is the use of coming up with just a different NP hard problem if our goal is to approximate? Well, it's the fact that there is a rather obvious relaxation for this integer linear program that will make it tractable. So what should I do to this integer linear program in order to make it tractable? Yes?
Have the x size be greater than or equal to 0?
That's not quite enough. I need to, or sorry, in this case it will be, but more generally, what might I want to do?
Between 0 and 1?
Yes. So instead of saying 0 or 1, I say between 0 and 1. In other words, I remove the integrality constraint. So instead, I'm just going to say that xi is between 0 and 1. Okay. So now I have a tractable problem. Unfortunately, in making it tractable, I also made it not any longer match the vertex cover problem. Right? I've relaxed the constraints. I have a larger solution space. I will now be able to find a solution that is not a vertex cover solution because it has fractions in the variables. Right? So, but again, I've at least made things a little bit more straightforward because I don't have to think about what the relaxation should be. Right? Once I write down the integer linear program, the relaxation is obvious. The question, of course, comes in the rounding. So suppose that we have solved this linear programming relaxation. So I have a bunch of fractional values. We need to take those fractional values and produce a vertex cover. And then we need to argue that this transformation from fractional values to integral values does not significantly perturb the value of the solution. Or we need to bound the amount of perturbation. Okay? So if I've got these fractional values, what would be a natural way to round them to integers? Yeah?
Take the ceiling.
I could take the ceiling, right? In other words, take every fractional value that's not 0 and make it 1. Okay? Now this will this work? Will this give me a vertex cover? How come? Why will this produce a feasible vertex cover? Yes?
Because in every edge, there is a non-zero value.
Right. I can't have a 0 on both endpoints of the edge. Right? That would violate this constraint. So somewhere there's a non-zero. So when I take the ceiling, I'll get a 1, and that edge will get covered. Okay? So that's a feasible rounding. But what can we say about its approximation ratio? Yeah?
Maybe bad.
Maybe bad. Right? I mean, right? I mean, linear programming likes to kind of spread stuff around. It's quite conceivable that every one of the variables will be positive. Right? You won't have any zeros at all. So everything will be rounded up to 1, take all of the vertices. So can we be a little bit more conservative in our rounding? Right? Do we have to round up everything that's positive, or can we do less? Yeah, back?
We round up everything that's greater or equal to 1 over 2 and round down the ones that are less.
Good. So in other words, we're going to round. Right? Is that going to give us a feasible solution? Yeah.
At least one of the xi or xj is to be bigger or equal to x.
Excellent. So again, we go back to this constraint, and we say, if xi plus xj is bigger than 1, then surely one of xi and xj is at least a half. Right? They can't both be smaller than a half. Right? So that tells us that we do in fact get a vertex cover. What does it do to the quality of our solution? How can we relate, right? When we sort of round things up in this way, right, what does it do to our objective function, the sum of the xi's? Yes?
It has to be in factor of 2.
We have to be within a factor of 2. How come?
Well, because we have the minimum, so we can go round up to 1/2, so the minimum.
Exactly. So we only round up. I'll call this xi hat. If xi is equal to 1/2, which means that we at worst double each xi, which means that we at worst double the solution. So we get a 2 approximation. What a surprise. Okay. Yes, a question?
Yeah, in our constraint, the structure of the constraint, it looks like we have at most 2 ones per column, because like if columns are edges.
That's correct. There are only 2 ones in each column.
So maybe we will have halves, like we won't have anything except halves.
Yes, well that's why I round up if I am greater than or equal to 1/2.
We'll never have anything between halves and 0.
Yes, so you're quite right. It may be that the fractional solution assigns value 1/2 to every vertex. But it is still true that we are at worst doubling, right? And so what that tells us is that the only time that we're going to take all of the vertices is if the optimum requires at least 1/2 of the vertices. Okay. Actually, there's more than you can say about this particular linear program. It's a very interesting structure. It's been studied a lot. It's called the stable set polytope. People proved that, in fact, in the optimum solution, there is an optimum solution where every variable is 0, 1/2, or 1. And they furthermore proved that if the variable is 0, then it does not belong in any vertex cover, any optimum vertex cover. If the solution is 1, then you might as well put it belongs in the optimum vertex cover. So the only ambiguity is for the variables that are 1/2. And for those, well, we take all of them because we can't tell whether they should be in the vertex cover or not. Okay, so this is a very, very interesting polytope that's been studied a lot in its own right. Okay, so we get a 2 approximation. So is this any better, any more useful than the greedy algorithm that we saw before? Well, this is kind of the problem where we get when we sort of move beyond analysis and into heuristics, right? These are approximation algorithms, and we can say they get within a factor of 2. Now, in practice, we might hope that they do far better than a factor of 2, but we don't have any proof that they do. So pretty much the only thing that you can do is try both algorithms and see which of them does better in practice. And honestly, I'm not sure which does. I mean, in general, these linear programs, when well designed, they sort of try to very closely track the underlying problem. And so if they capture a lot of the structure of the underlying problem, you would expect them to do relatively well. Yes?
You could also use software that solves it.
Absolutely, right? So if your problem is small enough, you can use brute force in order to solve it. And actually, in the brute force solving, it's really useful to have approximations. Because in brute force solving, you often want to try and prune a particular, like you do these sort of brute force enumeration, like we saw last time. You try all possible solutions in different directions. As you go, you might be able to prove, using these approximation algorithms, that there's no good solution down this path. So you can kind of prune off that path and avoid all of the work of exploring it. So that's another way that these sorts of approximation algorithms can be really useful, is that they can help you with branch and bound when you're trying to get exact solutions. Okay. There's another thing that this approach yields, which you don't get for in the super greedy algorithm. This approach also solves weighted vertex cover. So in weighted vertex cover, you're not trying to minimize the number of vertices. Each vertex comes with a weight, and you're trying to minimize the total weight of the vertices that you choose for the cover. So if I wanted to do that, how would I modify this approach in order to get a true approximation to weighted vertex cover instead of standard vertex cover. Yeah?
To xi over wi.
Where?
Like for xi plus xj.
So that is capturing a sort of a different problem, which says that if you want to use xi in order to cover the edge, you have to take wi copies of it.
The sum of the xi.
Good. So if our goal is to look at the overall weight, we can capture that in the objective function by just adding weight terms on the variables. Does this change the quality of my approximation? Do I still get a factor 2? How come? Yeah?
Xi is the worst case double. So
Yeah, my argument about worst case doubling is not changed by this weighting. And so the analysis goes through unchanged. This is not true, right? The greedy algorithm works great for unweighted vertex cover, but has no obvious generalization to weighted vertex cover. Okay. So the nice thing about this approach, using linear programming relaxations, is that integer linear programming is NP complete. In other words, every problem in NP can be written as an integer linear program. Right? That's sort of the definition of NP completeness, is this ability to transform between different problems. So every problem in NP can be written using an integer linear program. So we have a relaxation for any problem in NP, which is a pretty nice place to start. Right? Now, sometimes that relaxation is a good relaxation, and sometimes it's a bad relaxation. Right? Removing the integrality constraints from certain polytopes completely destroys them. It makes them into a completely different polytope. For other polytopes, when you remove the integrality constraints, you still get something that's a lot like the integer polytope. And so you can, if the polytope is similar, then that usually leads you towards an algorithm that can do a pretty good job of approximation. Okay? Yes, a question?
You just say that any NP hard problem?
Not NP hard, but any problem in NP.
Okay.
Okay. So NP hard just means it's at least as hard as NP, so that includes things that are outside of NP. Those can't be written as integer linear programs. But if it's in NP, then it can. Yes?
Can we get solutions where, like, the integer program has some value and you relax it gets arbitrarily bad? Like,
Yes, that's what I meant about how if you remove the integrality constraints, you may completely deform the polytope. Right? So it's not a deformation of the polytope, but the problem is, if you think about it, integer linear programming is sort of saying, I'm looking for a point in the polytope, but it has to be an integer point. So there's this sort of grid of points that are allowed, and only those points on the grid are allowed. And for this polytope, it appears that taking away the integrality constraints isn't too bad, right? Because when you find your optimum in the polytope, you're still going to be somewhere close to a grid point. And you could imagine that rounding will take you back to that grid point, and you'll do pretty well. Okay? Unfortunately, with your grid, you can also have polytopes that look like this. Right? Or that do capture an integer point somewhere, but the optimum is incredibly far away from the optimum integer point. And if the optimum fractional point has nothing to do with the optimum integer point, then it's very unlikely that you're going to get any information from it that allows you to find the optimum integer solution. Okay? So there are bad LPs, bad integer linear programs, and good integer linear programs. And interestingly enough, even for specific problems, there are different ways to write it down as an integer linear program. Some of the ways that you write it down will yield things that round well. Other ways that you write it down will yield things that round badly. And so in this approach, a lot of the cleverness involves picking the right integer linear program to start with. Okay? What is a good set of constraints that makes the fractional solutions kind of track the integer solutions? So let me give you a more involved example of this kind of LP relaxation for a problem known as facility location. So this problem dates back from the days before Amazon, when you actually thought about opening real stores to sell things. And the question was, where should you put them in order to best serve your customers? Okay. In particular, you're given the ability to open potential sites at cost fi. So there's a potential site I that you can open at cost fi. You also have customers, customers j, who can reach site I at cost Cij. Okay, and these might not be human customers, right? These could be oil refineries, and the customers are the gas stations that need to take delivery of gasoline from the refinery. They could be supply depots for anything imaginable. The point is that here you're looking both at sort of the cost of operating the facility and the cost of delivering from that facility to any clients that are using the facility. And you want to minimize the total cost. Where, of course, you can only use a facility to serve a client if you open that facility. So it's a sort of there's sort of two things going on. You're trying to decide which facilities to open, and then once you open them, which open facility to assign to each client in order to serve that client. Okay. So is the problem statement clear? Yeah?
Why wouldn't you just have each customer, is there some limit on the number of customers that can be served?
That's the capacitated facility location problem, which we are not going to study.
No, well, I guess I'm just confused as to why a customer would ever go to a facility where it has higher costs than the minimum.
They never would. So this is sort of something that we can observe right away about the solutions, is that once you've opened the facilities, it's obvious where every customer goes, right? They go to the closest facility. Okay? But this does not make the problem trivial, because we still have to figure out which facilities to open. Okay? Now, we are going to look at the metric version. Okay? That says that these facilities and customers are both located in a metric space where the triangle inequality is obeyed. Okay? So like TSP, this problem becomes very hard, I think intractable, if you are not putting on a metric constraint. Okay. So how do we attack this problem? Well, as I've hinted, the first step is to come up with a decent integer linear program that exactly captures the problem, then to relax that integer linear program to get something tractable, and finally to figure out how to round the fractional solution into a solution to the integer program. So what would make a good integer program? Sorry, did you have a question? Yeah.
What exactly is the triangle inequality?
So essentially it's saying that, so notationally it's a nightmare to write down because we have both customers and facilities, right? But if I don't talk about Cij's, but just say the distance from I to j plus the distance from j to k is greater than the distance from I to k, where in this, sorry, those are bad letters to use because they're already taken, AB, BC, AC. So for whatever combination of clients and facilities you want to talk about, right? So if there's a client A, his distance to a facility B, and then some other client C's distance to facility B, those together are greater than the distance from client A to client C. Okay? And vice versa for facilities. So if two facilities are both near a client, then they had better be near each other as well. Yes?
So is cost just like equal to the distance?
Yes. Sorry, this is the metric, the only metric that we're looking at here in terms of cost is the distance. That's what the triangle inequalities are on. Yes?
The triangle inequality, I don't know, it seems like it would follow from some kind of reseller model.
If you could allow resale, then sure. but often that's not possible in the problem that you're trying to solve. Right? The client may not have the facilities necessary to store and resell whatever it is that they're getting from.
Capacity constraints are occurring, so.
Absolutely. No. So as you might imagine, there are many different variants of this problem that you can consider. Okay, but we're looking at sort of the simplest, least constrained version of the problem. So problem definition clear? Yes?
I don't understand if we do not open any facility, then now this is
It is not, because you have to assign every customer to a facility. Right? You've got these customers. You have to serve them. I mean, again, there are variants of the problem where you're allowed to refuse to serve a customer. Right? But in the version we're looking at, every customer has to be served by some open facility. So let's write down an integer linear program. So let's start with the objective function. What's the cost of a particular solution? Well, actually, before the objective function, let's write down some variables. So taking a hint from the vertex cover, let's write yi to be a variable that is equal to 1 if you open facility I and 0 otherwise. And let's xij be equal to 1 if client j uses facility I and 0 otherwise. Okay, those are the choices we have. So now, with that in mind, what can we say about the objective function? Yes?
We're just minimizing fi yi plus sum over ij, cij.
Good. So if we open facility I, we have to pay for it. And if we assign client J to facility I, we have to pay for that. So this just comes right out of the definition of the problem. Now, what are the constraints? Yes?
Sum of xij over I for each j should be at least 1.
Good. So one constraint, as we just said, is that every client has to be assigned to a facility. Right? So some xij has to be 1. And writing that in terms of lower bounds, some xij has to be 1 just says the sum of the xij's has to be at least 1. Right? What other constraint do we have? Yes?
Xij is less than
Yes, xij is less than or equal to yi. What is that saying? What's the English interpretation of that constraint?
It means that I can connect the client J to facility I, if and only if it's open.
Exactly. I'm not allowed to assign a client unless the facility is open. And again, with zeros and ones, this is sort of clearly what it says, right? That xij being 1, that's only possible if yi is equal to 1. So I can only assign if it's open. And of course, we'll have the usual constraints that xij and yi are either 0 or 1. That's the integer linear program. And this integer linear program is an exact representation of the facility location problem. Right? If you can solve this ILP, you are solving the facility location problem. But we can't solve this ILP. So we are going to relax it. And all we do in order to relax it is change our constraint on the xij's and yi's to be that they should be between 0 and 1. Okay. So the relaxation is easy. The only challenge is the rounding. So any thoughts on how we might round? Yes?
Do we always take the ceiling for the yi variables?
Okay, so we could use sort of the ideas that we got from the vertex cover problem, that we should sort of round up, right? If we have a positive variable, then we'll turn it into 1, right? And this will certainly give us a feasible solution for the same reason as it did for vertex cover, right? We're not allowed to have all of the xij's be 0. Some of them have to be positive, which forces some of the relevant yi's to be positive. So we will be forced to open so that everything can be served. But this also has the same problem as for vertex cover, that we may be taking really tiny numbers and rounding them up to be huge. So the quality of approximation from that ceiling could be very bad. Right? And actually, things are a lot worse in this problem than in vertex cover. Sort of what rescued us in vertex cover was that really there were only 2 variables involved in a particular constraint, and so one of them had to be big. Right? So when we rounded, we only had to round the big variables up. Here, we have this very unfortunate sum of xij constraint. So we have many, many variables. So they could satisfy this constraint by having all of them be slightly bigger than 0. So now if we round up that way, we're going to have to worry about, we're going to have to round up things that are tiny. And so we won't be able to make the same sort of argument about quality of approximation. Yes?
We can round up the yi's, and for the xij's, we would greedily put the one with the smallest cij at 1.
Right, so this is absolutely correct. So really, we should only be worrying about rounding up the yi's, because once we've decided what to open, it's obvious how to assign, right? But we do still have this problem that if all of the xij's are just slightly positive, then it could be that all of the yi's are just slightly positive, which means bad ratio when we round things up. Okay, and so this is actually the sort of the challenge, is dealing with these very small numbers. Yes?
You could try to figure out which of the facilities are being most used by the solution, and then round those up.
Good. So this is a great instinct, right? Is that if we look at this fractional solution, if we have a facility that is barely open, then it really shouldn't matter very much, because every client needs a whole facility. So if there's just this barely open facility, that's only serving the client a little bit of what they need. Right? So there must be some other facilities that are serving the client. So we don't need to worry about this barely open facility. We could ignore it. Okay? And so that gives us a path towards ignoring the small y's, which is great, because if we only round up big y's, then we're getting a good approximation. Yes? Okay. So let's try to formalize that. So what we want to do is assign each j, each client, to some partially open facility where it has xij greater than 0, right? So if we start assigning, so we're trying to use the relaxation for guidance. So it would be really kind of weird if we took some client and assigned it to a facility that it wasn't using at all in the fractional solution. We're going to sort of say, let's use the fractional solution to steer us in the assignment. So take these xij's that are positive, and let's assign j to one of those. Now notice that the fractional, the relaxed cost, or the relaxed solution, it says that assigning j in the fractional solution costs what I'll write as cj, which is the sum of xij, cij. Right? So this is the fractional relaxation of the assignment cost for client j. Right? And you'll notice that this is showing up explicitly in the fractional optimum. Right? So according to the relaxation, this is how much it costs to assign client j. If we can round in such a way that this is how much it costs to assign client j, then we're in good shape, right? Because our cost of assignment is tracking the cost that is predicted by the relaxation. Yes? So what could be the problem with achieving an actual assignment to a single vertex, to a single site that has cost close to this fractional assignment? Well, the problem might be is if we have some tiny xij associated with a huge cij. Right? So, and this is coming back to the sort of the intuition that you articulated, right? The thing that can that sort of can make a mess is if the fractional solution is using a little bit of some really expensive assignment, but it's not hurting the fractional solution because it takes only a little bit of its capacity from there. Now, what's going to rescue us from this is that we're going to say, well, if it's only using a tiny bit, then we can ignore it. Okay? So what I'm going to rely on is that although there may be some outlier costs, we're going to be able to find something that uses just the average cost. Right? So this is sort of the average cost of assignment. And if we can do an assignment that's close to the average cost, then we're doing pretty well. So I claim that the fraction of i's with Cij greater than rho times the average cost is at most 1 over rho. So there may be a few slightly open facilities that are very expensive, but if I kind of rule out all of those very expensive slightly open facilities, that only removes a small bit of the facilities that client J wants to use. Okay. So why is this claim true? So for those of you who have seen it, this is actually the Markov inequality being written in a somewhat different way. But why does this work? Yeah?
Otherwise, the sum of the costs would be more than Cj.
Exactly. If I have more than a 1 over rho fraction, right, in other words, more than a 1 over rho amount of the xij's, costing each more than rho cj, then just that part of sum of xij cij is going to exceed cj. Okay. So if I detach those facilities, okay, all those facilities that it's too expensive to reach, just rule them out. Okay. So I still have sum over I of xij greater than or equal to 1 minus rho. Right? Sorry, 1 minus 1 over rho. Right? Okay, but now I've made the problem infeasible. Right? I no longer have a full unit of assignment for every client. How can I fix this without doing too much to the costs? Yeah?
Just scale everything up slightly.
Right. So I'm just going to multiply the remaining xij by 1 over 1 minus 1 over rho, which is rho over rho minus 1. Okay. So this is a step that is known in the literature as filtering. I don't know what, it's just the first person to publish picked that name. So you're filtering away the expensive destinations, and you get a new feasible solution. What does this do to the cost of the solution? Right? We had an optimal solution. We're now changing into a different solution. How much worse is our new solution than the old one?
Increase
Yes? Exactly. So this increases the assignment cost by a rho over rho minus 1 factor. Right? This is the same argument as we did with vertex cover, right? With vertex cover, we doubled the variables, and that only doubled the cost. Here, we're multiplying the variables by rho over rho minus 1, and that only multiplies the overall assignment cost by the same amount. Okay? All right, so now we're in good shape, because now that we have filtered out all of the destinations that cost significantly more than average, right? Any remaining destination costs less than rho times Cj, right? So if we look at the cost that the fractional solution is asserting, we can pick any one of the destinations that the fractional solution is offering and charge at most rho times Cj, rho times what the fractional solution thinks it's going to cost. Right? So that implies that the total assignment cost for whatever we pick is now going to be less than or equal to rho squared over rho minus 1 worse. Right? So if we pick some constant factor rho, we'll be losing a constant factor in the assignment cost. Yes?
What modeling are we doing?
No, so we're not, so we did this scaling up, right? And what I'm saying now is that now that we've done this filtering and scaling up, we can assign each client to anything where xij is positive. Because we've removed all of the things where xij is positive that have large cost. So we now assign to, whatever we do in the rest of the algorithm, as long as we do it with a non-zero xij, we're going to be at worst facing this assignment cost. Okay. So what's left? We've kind of taken care of the assignment cost, but now we've got to deal with the facility opening cost. Okay. So what do we say about facility opening? So here we pick up from what we were saying before, that we want to open facilities, and just like in vertex cover, if a facility already has a large yi, then opening it just represents multiplying that yi by a small constant. Right? Taking yi up to 1 is fine if yi is large. The problem is if yi is small, then that's a big scaling, right? And that's going to make it very expensive compared to what the relaxed optimum tells us. So we only want to scale up large yi's, but we have this problem that maybe all of the yi's are very small. Okay. So in order to deal with that, so the problem is if we have small yi's everywhere. Because then we can't really justify opening any of them. The solution that we're going to use is to find a clump of yi's, of nearby yi's, that have a total large. Okay, so if we find a whole bunch of facilities near each other that together account for one facility, right, then we can afford to open one of those facilities and let it cover the needs of all of its nearby facilities. So this is kind of a clustering step. We're going to break the facilities into clusters that all have one fractional facility in them, and then we're going to open one facility per cluster. Okay. In particular, once we have found a cluster of facilities that have sum of yi greater than or equal to 1, we're going to open the minimum cost facility. in that cluster. And so the cost of opening this facility is what I'll call F min, which, since the sum of yi's is greater than 1, is less than or equal to the sum of F min times the yi's, right? Which is going to be sum over the cluster of F min times yi's, which is, of course, less than the sum of Fi times yi in the cluster. Okay. Now, why is that a good thing? Well, this is the contribution of this cluster to the fractional objective, right? So if my cost of opening is less than what the optimum solution is talking about opening, then I'm doing a good job of keeping my cost close to the optimum cost. Okay. So now we're almost done. What's the problem if I'm only opening one facility in the cluster? What's the problem? Why can't I just sort of cruise on to having a solution to my problem? Yeah?
You're increasing the assignment cost a bit.
There's the assignment problem, right? So in the fractional solution, there was this whole cluster of facilities. They were all sort of fractionally opened. And there are clients of all of those different fractional facilities demanding different fractions of those different fractional facilities. Now I'm saying I'm not going to open all of those fractional facilities. I'm only going to open one of them. Okay. So what should I do with all of the clients who want to make use of some of the other fractional facilities? Well, the obvious thing to do is to reassign them to the facility that I opened, right? So I'm going to reassign any client of the cluster to this F min facility. Okay. So why, on the one hand, might that in general be a bad thing, but for our restricted version of this problem be not such a bad thing? Yeah? We have a metric. So in a general facility assignment problem where you have arbitrary assignment costs, telling somebody you can't go to this facility, you have to go to that facility, could cause an arbitrarily large increase in the assignment cost. But we're looking at the metric facility location problem. So things that are both near a client are also near each other. And so we can use this to argue that reassigning the clients to the facilities doesn't change the cost very much. So in particular, so here's the details. I am going to choose the client with the minimum value of Cj that has not yet been assigned. Consider all his available facilities. Available. And then open the cheapest and zero the others. And then, which this is the cheapest, this F min guy. And then assign to this F min any client using any zeroed facility. So is the statement of what I'm doing clear? Okay.
How does the objective function relate to the distance, to the metric?
Well, it's the metric that we're talking about is a metric over theCij's, right? That is the assumption is that theCij's form a metric. Yeah.
How does this capture that the facilities that you're like thinking about clumps of facilities that are close to each other?
So that is exactly so. I wanted to make sure that the statement of what I'm doing is clear. Now in the analysis, we'll see how that is captured. Okay? So what can we say? Well, first of all, notice that we looked at the cheapest. So the cluster that we're looking at, where we're choosing to open a facility, is the cluster of all the facilities that are used by client J. Right? So our cluster is all facilities used by client J. Okay. Well, that means that the sum of their yi's is at least 1, because that's one of the requirements of this linear program, is that every client has to have a whole facility available. Okay. And we sort of temporarily destroyed that by filtering, but then we fixed it by scaling everything up. Okay. So the sum of the yi's is greater than or equal to 1, right? And so as I was arguing on the other board, this means that the cost of doing this, of opening this fmin, is at most the sum of the fi's times the yi's in the cluster. So we're doing a good job on the opening cost. But now let's ask about the assignment cost. So let's consider some j prime that's using the cluster. And what does that mean? It means that some xij prime is greater than 0. Right? So consider some other client that has been partially assigned to a node in this cluster. What is its assignment cost? Okay. Well, the crux of the matter is that we can break it apart into pieces. So we're going to start at the client j prime. Okay. Now, he wanted to use some cluster node I. Okay. But instead, we closed node I, and we opened this other node, which was the minimum cost in the cluster. Now, what I'd like to argue is that switching this guy from I to fmin did not add very much to his assignment cost. How can I make that argument? Yeah?
I and fmin were both serving the same client.
Good. So I and fmin were both serving this client. So in other words, there's this j over here, okay, which had the minimum value of cj. Okay. So what we know is that this is less than rho times cj. And we also know that this is less than rho times cj. Okay. On the other hand, this quantity, from j prime to I, this is less than rho times cj prime. Right? But remember that we picked the smallest cj. Right? So here we have something which looks like cj prime, and here we have two other things which look smaller than cj prime. So at worst, we took this single copy of cj prime and we turned it into 3 copies of cj prime. And this is where we're using the metric property, right? That we're saying that that if I'm close to I, then I must also be close to fmin. Okay? So the total cost is in fact less than 3 rho times cj prime for assigning that other client j prime. Yes?
I'm a bit confused about when we're passing into integrality here.
We're passing into integrality right now, right? Because here is where I'm saying pick a particular node and pick a particular facility, open it, right? So that's passing to integrality. That's making a yi be integral. And now I'm saying assign every node that had a fractional value into this cluster, make it an integer value into this cluster. So assign every node that was partially using anybody in this cluster, assign them to this fmin node. And I just open this fmin node so I can assign everything to it.
And when we iterate on this for multiple clusters, we consider these already completely done.
Good. So that's the point, right? So now that I've done this assignment, right, Anybody who is using any fractional amount in this cluster has now been assigned. So anybody who's left, anybody who still needs to be assigned, is using all of their weight, all of their fractions are pointing to other nodes. So after I take away all of these facilities and all of the clients that are using fmin, what I'm left with is another problem that satisfies these constraints. So I can iterate this rounding procedure where I peel away a single cluster and a bunch of nodes all at the same time. Okay. So now we can put together these different pieces. So this is just sort of a summary. I multiplied each yi by rho over rho minus 1. I then multiplied the assignment costs by 3 rho. Okay. And so if I put these together, you balance these by setting rho equal 4/3, and you get a 4 approximation to both the assignment cost and the facility opening cost. And therefore, if you're approximating each of those within 4/3, then obviously you're approximating the total cost to within 4/3. Okay. More generally, you can vary rho, right, to be whatever you want. So if what you're concerned about is the total cost, and it turns out that the facility cost is much cheaper than the assignment cost, well, then maybe you should move more of the weight over to the assignment cost so as to drive down the overall cost. So this is, in fact, what's known as a sort of bi-criteria optimization problem, where really you have two separate quantities, the facility opening cost and the assignment cost, and you can kind of trade off the quality of solution to each of them. Okay. There's been plenty of additional research. And I believe, if it hasn't changed since I last looked, there's a 1.5 approximation that uses more sophisticated versions of these ideas. And also, there is 1.463 hardness. So this is a case where we're actually quite confident in the quality of our approximation, right? There's not a lot of room left to improve either the upper or lower bounds. We're pretty close to knowing exactly how well we can approximate this problem. Okay. Yes?
Is the 1.463 a special number of some kind?
Well, of course, it's not the actual number, right? There's more decimals. And it is the result of some weird equation that arises when you do the analysis of a particular reduction. Okay? Yes?
You say you multiply the assignment cost by 3 rho. Wasn't there like more stuff like earlier I got the rho squared over 1 minus 1, rho minus 1?
Oh, the rho squared. So it'll take me. So this is correct that you only need to multiply the y's by rho over rho minus 1. Let me not unpack it standing in front of you all, but let me sort of get it cleaned up, and I'll make sure that the notes reflect what's actually going on. Okay. Other questions? All right. It's late, but let's take a 2-minute break anyway, and then we'll do a little bit more. Deja vu here. I want to show you another very interesting rounding technique. And we're going to look at a problem we've seen before of set cover. Okay, so again, we have a collection of sets, and we want to find some of those sets that together cover all of the elements of the universe. Okay, so how do we write this as an integer linear program? Well, we're going to have variables xj if you choose set j. So this will be 0 or 1, right? And now we're going to have constraints that say that the sum over, let's see, elements I that choose set j. What? Yeah, so for each element, we want to say that it's covered. So we're going to sum a collection of xj's, and we're going to sum that over all of the sets sj that contain element I. Okay? That's going to have to be at least 1. So a very simple integer linear program, right? And of course, similarly, a simple fractional relaxation for the problem. How do we round this? That's where it gets interesting. So the vertex cover trick doesn't work. I mean, because as with facility location, there may be many sets that all contain an element, and they may all get small values of xj associated with them. So rounding up large numbers doesn't work. So we're going to use a different trick, which leverages the fact that these x's in the relaxation, these xj's are between 0 and 1. Okay. So anytime you see a real number between 0 and 1, there's something natural, a way to interpret that real number as something, namely a probability. Right? Any number between 0 and 1 can be a probability. So how can we use this sort of probabilistic interpretation? Well, we could talk about sort of the probability with which we choose set j. Right? And so if we're asserting that these x's represent the probability with which we choose xj, then what is this formula capturing? The individual xj's are probabilities of choosing sets, then what is the sum of xj's? Yeah? It's an expectation, right? So this is the expected number of sets that we choose that has that contain element I. Okay? So you can imagine a rounding procedure where we just flip coins according to these xj probabilities. And the reason that has some hope of working is because in expectation, every set is going to be covered. Unfortunately, it's not enough for every set to be covered in expectation. We want every set to be covered really. Okay? But suppose that we choose set j with probability xj. So we flip coins for each set. We take that set with probability xj. Okay. Now, in expectation, the amount that covers set I is 1. But we'd like to say something a little bit stronger. Okay? What we can say is that the probability that we choose some set covering I is greater than or equal to a constant. Okay. Why is that? Well, let's look at the complement probability, the probability that we don't cover I. Can somebody express that probability in terms of the variables on the board? Yeah?
Product of 1 minus xj, or j being there.
So it's the product over all of the sj's that contain I of 1 minus xj. Right? But this is less than or equal to the product over all of the sj's that contain I of e to the minus xj. Right? So this is the single most useful approximation in all of computer science. Okay? Going from 1 minus xj to e to the minus xj. Going from addition to multiplication. It shows up all the time. Okay? The reason is pretty straightforward. Right? We write e to the x. We write 1 minus x. And it's clear that e to the x is less than 1 minus x. Okay? So what's this product? All right, you want me to be more careful? It's actually over here, right? Okay. So what's this product? Well, this is e to the minus sum of the xj's. What can we say about that? Yeah? It's less than or equal to e to the minus 1 because we required the sum of the xj's to be greater than or equal to 1. So the probability that we miss a set is only a constant. What use is that? Well, if we do one of these trials, the probability that we miss a set is equal to 1 over e, or is less than or equal to 1 over e. Okay. Well, suppose that we do k trials. Then the probability that we miss a set is at most e to the minus k. Right? Now, if there are n sets that we want to cover, and we set e to the minus k times n to be equal to a half. Okay. In other words, k equals order log n. Okay. Then if we run k trials, right, so that the probability that any one set is covered is e to the minus k, we can conclude that the expected number of uncovered sets is at most how much? Well, it's equal to e to the minus k times n, so it's less than or equal to half. That's how I chose k. So if I run k trials, the expected number of uncovered sets is only a half. So now if we think back to that little dose of probability that we did for perfect hashing, we can now invoke the Markov inequality and can conclude the probability that we have an uncovered set is at most a half. So after doing this bunch of trials, we have a 50-50 chance of covering all of the sets. And all we did was flipped coins using the fractional variables of the linear program to guide us. Yes? What was that? Sorry, uncovered items. Yes, thank you. Sorry, some people look at the dual problem where you're picking items in order to cover sets. And so, okay, so this is a very simple example of randomized rounding. But again, randomized rounding is one of these sort of very generic techniques, right? You don't need to know anything about the specifics of the problem. As soon as the linear program produces numbers between 0 and 1, you should naturally think about what's going to happen if I randomly round the variables according to those zeros and ones. And what you'll see is often a situation like this one where sort of constants in the constraints turn into constant probabilities of satisfying the constraints. And so this technique works quite broadly. Yes?
What can we say about the approximation ratio?
So that's a very good question. So what did I do? In one trial, I picked every, so let's now ask, what about the number of chosen sets? So how many sets am I going to choose in one trial in expectation? If I choose every set with probability xj, what's the expected number of sets that I choose in a trial? Yeah?
Sum of the xj's.
So the number of sets that I choose in one trial is the sum of xj's. What is that quantity? Well, that's the objective, right? That's the fractional objective. Which is therefore less than or equal to the optimum, because we're working with a fractional relaxation of the problem. Right? So in each of these rounds, the number of sets that I choose is optimal. I just don't manage to actually cover everything. But if I do this log n times, then I do cover everything. And over the course of those log n trials, I picked optimum number of sets log n times. So the approximation factor is order log n. Right, more precise, if you work, I mean, it's actually the constant is 1. It's the natural log of n is the approximation factor that you achieve here. Okay, yeah?
So do you have to be a bit more careful with the fact that you're dealing with expected numbers of chosen sets as opposed to
Yes and no. So if I want to not be careful, I will say, well, in expectation, I am achieving a log n factor approximation, right? Which for many people would be fine. If you want to, you can say that the Chernoff bound tells me that with high probability I am achieving a log n factor approximation. I didn't want to bother to get into that level of mess in this analysis. Okay. Yeah?
You also need to think about using the markup at the end, because you're choosing the pieces where you did cover them all, and then those could have used a lot of sets.
Actually, I would probably phrase it in terms of a waiting time until I cover everything instead, and not in order to avoid conditioning. But we can talk about the details of that if you like. OK, so yes?
This seems to be a randomized algorithm. Is there a way to...
Yes, this is a randomized procedure. But so I should point out, we already had a log n approximation. Now we got another log n approximation. Again, not clear which is going to be better in practice. This one, I would put my money on this one because it's more closely following the problem than the greedy algorithm, but who knows? Can we do better? No. There is a hardness result that says that you cannot do, and actually it's a constant of 1. So this algorithm achieves natural log of n, and it has been shown that you cannot do better than natural log of n. No constants at all, right? So basically we're tight on how well we can do this. So this ends our study of approximation algorithms. On Wednesday, we'll start in on online algorithms. Now a question. I may want to run a little experiment on you all. Is there anybody who would have a problem bringing a laptop to class on Wednesday? No? OK, good to know. Keep an eye on your emails.